Let's talk about one of the absolute wildest predictions from Einstein's general relativity. It's this idea that the universe isn't some static, empty background for everything. Nope. It's a dynamic fabric that can actually be twisted and dragged around by massive things like planets. It's a concept that really messes with how we think about space itself.
Okay, to really wrap our heads around this, let's start with a little thought experiment. Imagine you have the most perfect gyroscope you can possibly build. You stick it in orbit around the Earth and you point its axis at some really distant star. Now, here's the question. Will it just stay pointed at that star forever?
I mean, our gut feeling, our intuition, just screams, yes, of course it will. It's a gyroscope. Its whole job is to keep pointing in the same direction. But Einstein's theory of general relativity gives a totally different, and frankly, pretty bizarre answer. No. It says the very fabric of space-time around the Earth is going to grab that gyroscope and force it to drift.
And that's what makes this whole thing so profound. You see, a gyroscope, because of this neat principle called the conservation of angular momentum, is the perfect tool for this test. It's literally designed to fight any change in its orientation, which makes it the ultimate measuring stick for what's happening to space itself. So why on earth would it drift? Well, Einstein's theory actually gives us two reasons. The first one is kind of like a cosmic curveball that's thrown by gravity. The technical name for this is geodetic precession. And here's the key idea. Massive things, like our own planet Earth, don't just pull on stuff with gravity. They actually bend and warp the fabric of space-time around them. And just moving through this curved space is enough to make our gyroscope start to turn.
You've probably heard the classic analogy. Picture a heavy bowling ball sitting on a big, stretched-out rubber sheet. The ball makes this deep dent, right? Well, if you try to roll a little marble past it, it won't go in a straight line. It's going to follow the curve in the sheet. Our gyroscope is basically that marble, rolling through the dent that Earth makes in spacetime.
And this effect adds up. As the gyroscope makes one full trip around the Earth, cruising through this warped spacetime, its axis gets nudged, just a tiny bit. By the time it gets back to where it started, it's no longer pointing at the exact same spot it was. So just how big is this nudge? Einstein's math predicted a drift of about 6.6 arcseconds per year. Now, an arcsecond is an incredibly small slice of a circle. There are 3,600 of them in just 1 degree, so it's a super small effect, but it's actually the bigger of the two we're looking for. But that curveball, that's only half the story. Now we get to the second part, and this is where it gets even more mind-bending. Let's talk about the space-time twist. You see, the Earth isn't just some static bowling ball sitting still in space. It's spinning, right? It makes a full rotation every 24 hours. And according to Einstein, that spin should have a totally separate and even weirder effect on the spacetime all around it.
They call this effect frame dragging. The idea here is that a rotating object doesn't just curve spacetime, it literally grabs onto the fabric of spacetime and twists it, creating this kind of cosmic whirlpool.
Probably the best way to picture this is to imagine the Earth spinning, but submerged in a giant vat of really thick honey. As the Earth turns, it's going to drag the honey closest to it right along for the ride. Well, in this analogy, space-time is the honey. The Earth's rotation is literally dragging the universe along with it.
So you really have two different things happening. On the one hand, you have the simple dent in space-time caused by mass. That's the curve, the geodetic precession. But on the other hand, you have this twisting vortex caused by the planet's rotation, and that's the twist, or frame dragging. Two totally distinct predictions from one incredible theory.
So how much of a twist did Einstein predict? A minuscule 0.041 arcseconds per year. I mean, that is more than 150 times smaller than the geodetic effect, which was already tiny. Trying to measure this was going to be one of the hardest experiments in the history of physics. So how in the world do you prove something that subtle? Well, you launch one of the most ambitious and technologically insane missions ever thought up, Gravity Probe B. This satellite, launched back in 2004, was designed for pretty much one purpose: to put Einstein's predictions to the ultimate test. And inside, it carried 4 of the most perfect gyroscopes humanity has ever managed to build.
And when I say perfect, I really truly mean it. These things were spheres made of pure quartz and silicon. They were so perfectly round that if you blew one up to the size of the entire Earth, the tallest mountain on its surface would be just a few feet high. That's the mind-boggling level of precision we're talking about.
The challenge for this mission was just monumental. Step 1, build the world's most perfect spheres. Step 2, launch them into an exact polar orbit. Step 3, shield them from literally every possible disturbance. Heat, magnetic fields, you name it. And then, Step 4, measure a change in direction that's so small it's like measuring the thickness of a piece of paper from 100 miles away. Just staggering.
So, the probe locked its gyroscopes onto its guide star, and then, for more than a year, it just watched. It was hunting for two things: that larger drift caused by the curve in spacetime, and that almost impossibly tiny drift at a right angle caused by the twist. After years of painstakingly analyzing every scrap of data, filtering out every possible source of error, the team at Stanford and NASA finally announced what they found. This was it. This was the moment of truth for Einstein's wild idea.
And the result? It was a perfect match. Gravity Probe B measured a geodetic drift of 6.606 arcseconds and a frame dragging drift of 0.039 arcseconds per year. Both measurements were in spectacular agreement with what Einstein had predicted almost a century earlier. He was right.
What this experiment confirmed were two fundamental rules of our universe. Mass tells spacetime how to curve. That's the dip we feel as gravity. But rotating mass does something extra. It grabs spacetime and tells it how to twist.
So what this really means, the big takeaway, is that the universe isn't just happening on some fixed, invisible stage. Spacetime is a real, physical thing. It's an active player in the whole cosmic drama, constantly being bent, stretched, and dragged around by the dance of matter and energy.
The success of Gravity Probe B was a huge victory, confirming one of the most profound ideas in all of science. But it also leaves us with this one tantalizing final thought. If the very fabric of reality can be curved and twisted, what else can it do?